Oh. Hey, everybody. Hey. Gleb Alexandrov here, and welcome to yet another very exciting presentation. Today we're going to be talking about 3D Nebulae and the power of the Blender community. So yeah, my name is Gleb. I'm a 3D artist and a Blender YouTuber, if there is such thing. And together with ID Burrows, we run the Creative Shrimp blog with tips and tricks about computer graphics, art, and coffee brewing. And usually we include some kind of a music jingle before our tutorials. So I wanted to recreate this special kind of ambience just for you here.
With coffee and tea, presentations in 3D. Started with a blimp, it's Creative Shrimp.
Thanks a lot. Yeah, so why space, why Nebulae? Because space is awesome, of course, but also in 2017 we released Space VFX, the ultimate guide for creating galaxies in Blender. And it went pretty well, but one thing that was missing was volumetric clouds and that sort of stuff. Of course, we papered over the cracks and we used various two-dimensional techniques to create an illusion of depth, but in the end, it was just an illusion. And we've been wanting to play with the same toys as other folks who use proprietary software, like massive particle systems with millions and billions of particles. Fully volumetric objects that you can fly your camera around. That sort of stuff. And let's say it, we couldn't do anything like this in Blender. And if you jump back to 2017 with me, you would discover that we can do nothing like that in Blender, and traditionally that area of computer graphics was dominated by proprietary software, and for good reason, you know. And on this pie chart, we left just 1% of the Krakatoa-style Nebula simulations to the open source software. And but unsurprisingly, most of the Krakatoa-style simulations, and the Krakatoa is the render engine meant for that kind of stuff, was made in Krakatoa. Here you can see amazing art by Tion van der Zalm, Vyacheslav Pozavac, Martin Mirola, other amazing artists. And like 99% of such stuff was indeed produced in 3ds Max and rendered in Krakatoa, or it was Houdini. And how could we even compete with that? How could Blender catch up with that? So let's take a look. My hypothesis is that we could use the power of the Blender community, of the open source, open collaboration to cross the divide, you know? So first of all, we've been donating money to make Blender better. And I mean all of us, not we, but all of us, and some corporations. So we have been donating money, but in 2018, we did something amazing. Basically, the Blender user base crowdfunded the CodeQuest project to fly developers to Amsterdam, lock them in the room, and make them work for the common good. And hopefully that would lead to improvement in all areas of Blender and in volumetric rendering, right? So without the never-ending support of the Blender community, it would be highly unlikely that, for example, 16 developers could work on improving Blender and improving volumetric rendering. So, for example, Clement Foucault could come and single-handedly code something like volumetric rendering system for Eevee, for the new real-time render engine. So when I think about it, that's insane. Now we have like real-time volumes right in your viewport. That's the holy grail of 3D rendering, and now we have it. So that, I think, is pretty damn insane. So, since 2017, we got about 120 code commits directly related to volumes and volumetrics. like principled volume shader coded by Brecht van Lommel and other amazing features and, most importantly, bug fixes and stability improvements. So now you can, for example, have like amazing improvement coded by Kevin Detrick, cycles, volume, fast empty space, optimization, whatever. But every improvement like that made Blender render volume metrics a bit faster. So all in all, like now we can enjoy about 100% faster Blender in relationship to volumes. And if we factor in the hardware growth that occurred naturally over the years, so we can say that it's like 3 times faster or something like that, which is representative of switching from the video card of the previous generation to the mainstream gaming video card of the current generation, plus the bug fixes and the performance improvements coded by the amazing Blender developers. So, is it enough for us to render amazing Krakatoa-style nebulae? I would say kind of yes, but also no. Something else needs to happen. And I want to show you the volumetric slice of the interactions within the Blender community. No pun intended. I want to show how people talk to each other, share ideas, and generally ping-pong ideas of each other to create something unbelievable. And on the right, you would see the progress bar. At the top, there is the Krakatoa mark, so the ultimate goal. Of course, I'm a little bit biased. I consider myself to be a part of this community, but I will try to keep it reasonable. So, let's start with 80 Burrows. 80's procedural patterns took us through the initial stages of research. I mean, the stuff we designed for original space VFX. Procedural noises in Blender are like generators of everything, especially if you combine a few noises together. You can quickly create patterns that resemble astronomical objects like nebulae, all right? And what I like about procedural noises is that they have built-in infinite details. So you can fly right into the cloud, right into the noise, and see the new levels of details unfolding right in front of your eyes. The standard Blender noise, in other words, the Perlin noise, gives you that opportunity to experiment with all kinds of patterns and to have built-in fractal-like details. All right? And right at that time, somewhere in the depths of the Blender Artist Forum, Benny Govertz invented a pretty clever way of utilizing 3D textures, 3D patterns, to plug it into the emission shader, then into the volume input of the material to create a volume light in the most literal sense of the word. And it already looked almost like an emission nebula if you think about it. And so we took it a step further, and after playing a little bit with the volume light, plugged it into the volume shader instead. And that's how it goes. So basically, you take a cube of volume light, and you can play with the density, or rather the strength of that light, by utilizing three-dimensional noises of Blender. And you can combine a few noises together if you want to create a slightly more detailed noise. And after playing with the color ramp to colorize it, you would discover that you created something that looks roughly like an emission nebula. Let's marvel at the beauty of the universe for a second. And then you just recombine it with the volume shader instead to get juicy features of the volume shader, like absorption, scattering, anisotropy, and other physically correct properties of the volume shader, of the principled volume shader coded by Brecht van Lommel and inspired by Disney. So you will get something like a dust cloud. And we knew that we were on the right track when the grandmaster of the nebula design, Tion van der Zalm, gave us a tap on the shoulder and said that it looked just like particles. And I think that was the point, because we were aiming for that kind of look. Bam, the B3D factor kicks in, the community-generated progress. You'll be seeing this a lot. And back to particles. Juan Gia optimized the particle generation so we could play with more and more particles on screen. And when Gottfried Hoffmann noticed it, he just removed the hard-coded particle limit altogether. And after ping-ponging some ideas with Gottfried, we invented a pretty interesting way of utilizing the inherent motion of the particle system to apply motion blur and create an impression that there are more particles on screen than there actually are. Not only that, but Gottfried also wrote a script that froze time, so we can fly our camera around this constellation. And if you think about it, that's pretty insane. We had a static nebula, which showed motion blur due to the motion of the particles within the cloud. That is pretty cool, I think. And yeah, Gottfried, it's for you. But particles are fun only when combined with physical forces. So we watched many tutorials on the Blender side of YouTube. Thankfully, you could find anything you want there. The Blender tutorial business was and is booming. So we watched a bunch of tutorials, including the tutorials by Iago Motta. The best we could find. Iago's tutorials were like insanely valuable for us. We were able to familiarize ourselves with that aspect of Blender like in no time. And we were excited to try that out for our own stuff, for our own nebulae. So I would like to show you a few demos that we managed to create without actually burning our computer, because smoke simulation was fun. The shapes that it produced looked pretty neat, but at the same time, it had a bunch of problems. Like, well, the biggest problem was the problem of the resolution of the smoke. Unlike procedural texture, you didn't have built-in infinite details. So we needed something to push it to the next level. And we thought about stuff like volume displacement in Arnold render engine that could help us to do that. And volume displacement does exactly what it says on the tin. It takes the volume and it displaces it using some kind of a texture. And we even wrote to Ton Rosendahl asking whom do we have to bribe to get this feature in Blender. And as it turned out, Brecht van Lommel would be willing to check on this in the coming days. Yay! But we wanted it now. So after talking to Robert Schutze, we discovered that Robert coded a little Blender Cycles volume importer that allowed us to import volumetric data from Houdini and other applications supporting OpenVDB as slices, as two-dimensional images that then got recombined within Blender, within the shader, to create a three-dimensional representation of the smoke or of the nebula in our case. That was pretty cool. But we didn't know how to properly install OpenVDB library for Blender to be able to export stuff from Blender and then import it back. And then do these things like distorting the UV input and displacing the cloud to add extra details. So yeah, we put it on hold. And instead, Gottfried proposed to use the point density shader. The point density shader indeed worked just like volume displacement when you think about it. Let's see how it works, actually. I want to show you. So first, you run this smoke simulation. This one is, by the way, controlled by the turbulence force field. And then you add some particles, and you make particles follow the smoke using this smoke flow force in Blender. And then you turn these particles into tiny volumeric points in space or voxels using the point density shader. But it looks cool and detailed, only surprise when combined with procedural noises. And let's strip it down and actually see how it looks without any enhancements. Let's get back to its initial form. And you will see that it's a bunch of voxels floating in space. And then let's get back our resolution and zoom into the cloud just a little bit. And you see, bam, no details whatsoever. Let's distort it using the noise. Now we have details, right? But it was pretty unstable. I would say unstable as hell. So we decided that instead we would come back to our comfort zone. And thankfully, right at that moment, Simon Thomas, a node genius, a math genius of Blender, released a procedural noise pack which had this amazing advanced noise group, which worked pretty well when combined with volume shader. It had the right balance of big, medium, and small shapes, and we don't have to understand how it works. Basically, it's a bunch of noises combined to create a sort of a mega noise, which produced pretty interesting patterns when plugged into the volume shader, because every kind of noise in Blender is three-dimensional. It works perfectly with volumes. And this noise in particular helped us a lot and empowered us to keep experimenting with that technique of rendering volumetric objects with procedural noise. That is the default cube, by the way. And let's zoom into it a little bit, and you will see that it holds up pretty well, because the details given to you by the procedural noise work with volumes perfectly. And Omar Imara took it to the next level by extending all the Blender noises, I think, or was it just the Perlin noise, to other dimensions, namely to the fourth dimension, which is time. So we could play with the evolution of the noise, which would shift over time. That is pretty incredible. Omar did it during the Google Summer of Code. That is really, really great and really helpful. Boom! B3D factor goes up yet again. Another branch of deep space research was aimed at fractals. Fractal is a never-ending pattern, infinitely complex pattern that could be very useful indeed for simulating infinitely complex formations like nebulae. So Jonas Dichel was the one who showed us how to do fractal math in Blender. Jonas not only produced absolutely incomprehensible, great tutorial, but also he shared the blend file. And we picked that blend file, did practically nothing with it because our math knowledge wasn't up to this task. But anyway, it was great, and now everyone can try to render fractal in Blender, which is pretty neat. And Robert Schutze also experimented with fractals. Basically what he did is he took a WebGL playing marble shader or whatever, and he recreated using Blender nodes. So, for example, we could take this shader and render, infinitely complex stuff like a tiny universe inside the box. It's amazing, right? Yeah, a round of applause for Robert. Yeah, you notice the spaghetti monster going on, and you don't have to understand how it works. It just works. It's a fractal. But have you ever tried art direct in a fractal? Yeah, you don't have to answer because it's nearly impossible, you know. And so, incidentally, Robert also coded a custom internal volumetric sampler, or whatever it is, which allowed us to calculate fractals 4 times faster, right out of the box. Boom, community-driven progress. Sweet, sweet open collaboration. Back to procedural noises. Thanks to the Simon Thomas noise and just to Blender default noises and procedural patterns, and thanks to the principled volume shader coded by Brecht van Lommel, we managed to arrive at the patterns, at the astronomical-looking objects that we really liked, that really resembled the real stuff. But surprise, it was slow, because volumetric rendering can be slow in general. And default Blender denoising didn't do a great job with it. So the game kind of changed when Grant Wilk released the denoise add-on that brought the NVIDIA's optics, artificial intelligence-based denoising to Blender. It performed in a much better way than the default 2.79 denoiser, especially in such insane cases like the particle system and low resolution, stuff like that. And we got dramatic performance boost at the cost of insane rendering artifacts, especially in animations, because the denoiser processed each frame slightly differently, so the animation was jittery in the end, but we could live with that. And thankfully, right at that time, Stefan Werner also added the Intel OpenImage denoise to Blender, which wasn't hardware specific, because optics only worked with NVIDIA video cards. And yeah, the Intel OpenImage denoise was as magical as optics. It simultaneously appeared in many places, including the theory build. So hopefully by now you can see how the Blender user base, like a hive mind, have been making the prospect of rendering amazing three-dimensional nebulae in Blender a bit more real. So, for example, we can sprinkle it up with the creative shrimp magic and render something like that. That is, by the way, Cycles, a good old path tracing render engine of Blender. I want to show you a few demos and take a sip. Yeah, thank you so much. And then Eevee came out, and it changed the game once again. And Eevee, obviously, is the semi-real-time render engine, which supports volumetric rendering now, thanks to Clement Foucault and other amazing Blender developers. And so the Blender community rushed to port their space objects to Eevee. Yeah, and just within a few months after the official 2.80 release with the support of volumetrics, we got dozens of renders by Brent Patterson, dozens of amazing blend files shared, and sharing is at the heart of the Blender community, is at the heart of the open source movement. It's very useful indeed to have access to all the files. Like, we got amazing breakdowns and resources by Curtis Holt. Andres Steffens invented a clever Z-depth hack that paved the way for the smoother-looking animations. Mark Kingsnorth released a Nebulae generator add-on and some amazing artworks. Gottfried Hoffmann did something again, because Gottfried was pretty active during that research process. Stefan Wink absolutely killed it by sharing real-world, or rather, should I say, real universe example of pillars of creation rendered in Eevee. And on the left, you can see Eevee render, which took 3 minutes, and Cycles render took 40 minutes. What would you prefer? Hey, and I want to show a few Eevee demos now. Yeah, actually, if that is not impressive, I don't know what is. Just within a few months after the official 2.80 beta release, we moved from 0 to the pillars of creation type of nebula, seen right in your viewport, almost in real time. Oh my goodness. But even though Eevee has been maturing very fast, boom, progress. It was yet to beat Cycles in terms of raw visual fidelity, in terms of details and physically correct light transport and that sort of stuff. The best nebula we created so far were created in Cycles with some Eevee help. But it took a long, long time. One frame could render for 6 hours or more on an average video card. And 8 seconds of animation could easily take 50 days to render. And that made us sad, because we wanted to render animations. And on an average render farm that could take up to $4,000, something like that. That made the doc really sad. And so what could we do? What could we do? Yeah. Actually, we asked people, and the people responded once again. And we did our own research as well, but the Blender community was unbelievably helpful during that process. So I won't be bothering you with all that stuff, especially we're running out of time, but Stefan Werner suggested us to use LightPath Node to kill the details in the shadows and optimize our Nebulae this way. Derek Barker just sent me the link to the custom theory build that out of the box gave us 1.0, whatever, a huge boost in performance. Thiago de Sul shared a pretty clever hack of disabling the ray visibility of every ray except the camera rays, because the Nebulae doesn't interact with anything else in the scene except themselves, so we can disable all the rays and get our much wanted performance boost. We changed, that was very clever, we changed the aspect ratio to make it slightly more Panavision, to cut the top and bottom of the image and optimize it this way, and we removed 7 Yeah, I know that is phenomenal. I know, don't clap. That is, I know, that is genius. And we removed 7 light sources out of 9, because you can always optimize it a little bit more. But now, hold on to your chairs. Do you know what eCycles add-on is? It's a wonderful add-on that is basically a supercharged version of Cycles. And the creator of the add-on, Matthew Manuel, shared a custom build of eCycles specifically optimized for Nebulae rendering, for volumetrics. It had just one checkbox, Nebula optimization, something like that. And it gave us a huge, immense boost without altering the quality. Like, think about it. And in some scenes it was 30%, in some other scenes it was, this is the checkbox, by the way. In other scenes it was 16 times faster. Yeah, with some loss in details, but anyway. And we hoped, incidentally, the new version of eCycles is released today. We hoped that Linux would bring another competitive edge in terms of GPU rendering performance, as suggested by Steve Lund and other folks from the community, but we got a mixed bag of results, and we decided not to hurry up too much. And crazy stuff. We hoped that Andy, aka Deep Blender, would release a super resolution add-on for Blender that would allow us to render in 50% of the resolution and upscale everything to the original size without the quality loss. But yeah, I hope that one day he will do it. Yeah, and my brother, Roman Alexandrov, implemented even more shameless hack. So basically, he coded the Optical Flow plugin for Blender. Do you know what optical flow is? Basically, it allows you to slow down the sequence, the video sequence, smoothly, without stuttering. But if you can slow it down, and it's usually used in After Effects and DaVinci Resolve, you can skip frames. Like, you can render each third or even each fourth frame and speed up your rendering by 400%. And then you can reconstruct all the frames using the optical flow algorithm. And in some cases, you would even get away with it. And so, yeah, we got another performance improvement, which was about, I believe, an average type of scene. We skipped just every second frame, but anyway. So, yeah, multiplied by 2 or by 5, bam, the B3D factor goes up once again. So by squeezing every bit of performance out of Blender and by picking the community brain, by sprinkling it with the creative shrimp magic, by utilizing techniques originated within the community and performance optimization tips, custom builds like Theory build or eCycles Nebula build, we managed to move from 6 hours per frame to much more manageable figures. like less than 20 minutes per frame. And that meant that we could render this stuff overnight, the preview animation. I want to emphasize in the preview quality, but yeah, we could render it. And that meant that we could submit it to render farm, and it wouldn't cost us an arm and a leg, because now it became possible out of a sudden. Thankfully, such thing as distributed rendering has become a viable option. Distributed rendering means that people share their computers to do rendering tasks that would otherwise take weeks and months to finish. Probably the most popular distributed render farm is Shipit. And to give you some details about Shipit, 100 million frames rendered since 2012, up to 700 machines simultaneously rendering each day. 1,000 years of Blender projects since 2012, including our Nebulae. Special thanks to Brent Patterson for helping us out with rendering this stuff on Shipit. So yeah, it could take 5 months, 7 Nebula sequences to render on 80's PC, and it took 3 days to render on Shipit, with approximate cost of 5 million Shipit points. I'm not sure about the carbon footprint. I'm not qualified to talk about that. But anyway, it was very satisfying to watch how people connect their computers to help us render this stuff out. And did I say that I will show the amazing demo reel at the end of the talk? Did I? No, not really? I will. I will squeeze the duck, and there is a special button inside, and it will launch the demo reel. So get ready. Okay, thankfully, not only free render farms, collaborative render farms have been changing, but also commercial ones. So render farms like Render, which had distributed infrastructure, allowed us to have pretty competitive prices, like $0.5 to $0.75 per hour, thanks to the nodes scattered worldwide. It worked kind of like Uber for rendering, yeah? So we rendered, I think it was 4 sequences on Rays, 200 hours versus 1 hour. It costed us something like $140, which is not bad, I think. So with the help of collaborative rendering and commercial render farms, we pushed it to 11 out of 10. And I don't want to disappoint you guys, but I don't think we quite reached the proprietary software level, the Star Trek end credits quality, but not that we wanted. And yeah, it's not an arms race, and I don't think that the actual state of affairs is as important as the trend, and the trend is pretty clear to me. And now I want to give you a very exciting demo reel indeed. So can you count from 10, or let's say from 5 to 1, okay? 5, 4, 3, 2, 1, go!
Wait, hold on a minute, Gleb. Can you see me? Oh,
goodness
a
gracious.
Slightly bigger theater this year. Nice. Look, I don't mean to intrude, but since I am Captain Disillusion, world's greatest blenderer, and outer space is kind of on brand for me, I think I should be the one to press the button that starts the demo.
Okay, it makes sense. All right.
Great. Of course, in order for my signal to reach all the way to your laptop from here, I had to rewire a few things again and give it more juice. So get ready for the ride of a lifetime. Here we go. 1, 2, 3. Okay, how about I just show you the view out of my window instead?
Volume all the way. Yeah, thank you so much. Thank you. The duck loves you all. Yeah. Yeah, I'd like to thank so many people who have been helping to push this stuff forward. The duck adores you all. And yeah, thank you very much indeed.
With coffee and tea, presentations in 3D. Started with a blimp, it's creative shrimp.